The worst-case scenario for 3I Atlas sounds insane until you consider this. What if it's not following its predicted trajectory anymore? What if the course deviation detected on September 17th, 2025, is actually a correction maneuver executed by technology we can't detect? Imagine an intelligence so advanced that altering trajectories without visible propulsion is child's play. A civilization that deploys assets capable of mid-flight navigation adjustments, disguised as gravitational perturbations or outgassing events. 3I Atlas's unexpected trajectory shift and the timing of this maneuver might be signatures not of natural orbital mechanics, but deliberate course correction. As astronomers scramble to recalculate its path, sophisticated systems could be fine-tuning approach vectors, preparing for an arrival we never anticipated. Tonight, we'll venture into the speculative shadows where Keplerian mechanics crumble and navigational paranoia takes root. The question isn't whether 3I Atlas shifted course. It's whether that shift brings it closer to us. Part 1. The discovery that changed everything. On September 17th, 2025, the Catalina Sky Survey detected an anomaly in 3I Atlas's position. The interstellar comet appeared 0.2 arcseconds off its predicted trajectory, a small deviation by astronomical standards, but statistically significant enough to trigger immediate follow-up observations. Within 48 hours, both the Gemini North Observatory in Hawaii and the European Southern Observatory in Chile confirmed what astronomers had hoped was merely measurement error. 3I Atlas had changed course. This represents the first observed trajectory deviation in a confirmed interstellar object. Oumuamua, discovered in 2017, showed continuous, non-gravitational acceleration that puzzled scientists for months, but maintained a predictable hyperbolic path once that acceleration was factored into models. 2I Borisov, detected in 2019, behaved exactly as a typical comet should, following Keplerian mechanics with textbook precision. But 3I Atlas has done something neither of its predecessors did. It has executed what appears to be a discrete course change. The technical specifications paint a picture of an object that has defied expectations from the moment of its discovery. Originally detected by Chile's Atlas telescope on July 1, 2025, 3I Atlas was calculated to be on a hyperbolic escape orbit with perihelion, its closest approach to the Sun scheduled for October 29, 2025. Its closest approach to Earth was predicted at 1.8 astronomical units, approximately 270 million kilometers, nearly twice the distance between Earth and Mars at their closest. The deviation detected in September shifted its position by approximately 15,000 kilometers from where orbital mechanics suggested it should be. The shift occurred sometime between September 15th and September 18th, detected during the gap between observation sessions. Its velocity remains unchanged at 132 kilometers per second, but the direction of that velocity has altered by approximately 0.3 degrees. Despite this dramatic trajectory change, a nagging question persists. What if natural explanations only scratch the surface of what we're witnessing? NASA's Center for Near-Earth Object Studies responded swiftly to the discovery, issuing a preliminary assessment within 72 hours. Their statement, carefully worded and scientifically conservative, emphasized that the deviation falls within expected parameters for cometary outgassing and poses no increased threat to Earth. The agency's position is unequivocal. Even with the course change, 3I Atlas's closest approach remains beyond 1.5 astronomical units. No trajectory models, regardless of how the deviation is interpreted, suggest any possibility of an Earth intersection trajectory. In fact, the shift appears to angle the comet's path slightly away from the ecliptic plane the flat disk in which Earth and most planets orbit. JPL's Sentry system, which continuously scans for potential impact threats, shows zero probability of Earth impact. The European Space Agency's risk list, maintained independently, shows no elevated concern. Yet beneath these mathematical certainties lies an uncomfortable reality. We've never observed an interstellar object alter course before. Is this deviation genuinely unprecedented, or have we simply never had the instruments to detect such maneuvers until now? The Hubble Space Telescope and James Webb Space Telescope have provided additional context to the deviation. Hubble detected increased coma activity, the cloud of gas and dust surrounding a comet's nucleus, beginning approximately 3 days before the trajectory shift was detected. JWST's infrared spectroscopy revealed elevated carbon monoxide emissions during the same period, along with a surface temperature increase of 15 to 20 Kelvin. These observations appear consistent with asymmetric outgassing events on the comet's sunward side, where solar radiation heats volatile materials, causing them to sublimate and escape into space. The escaping gas creates thrust, much like a natural rocket engine, capable of altering a comet's trajectory. But when we venture beyond NASA's careful language into the realm of speculation, what shadows might this course correction cast on our assumptions about passive cosmic objects versus actively navigating ones? The conventional explanation holds considerable weight. Comets are known to exhibit non-gravitational forces due to outgassing. As a comet approaches the Sun, solar radiation heats its surface, causing frozen materials, water ice, carbon dioxide ice, methane, and other volatiles to transition directly from solid to gas. If this outgassing occurs asymmetrically, with jets of material escaping preferentially from one side of the nucleus, the reaction force can alter the comet's trajectory. This process is well documented in solar system comets and was eventually accepted as the explanation for Oumuamua's mysterious acceleration after months of scientific debate. Yet, this conveniently timed outgassing raises an uncomfortable question. What if the chemical signature we're interpreting as natural sublimation is actually propellant exhaust from a technology that mimics natural processes? The correlation between increased activity and trajectory change certainly supports the outgassing hypothesis. 3 days of elevated coma production, followed by a measurable deviation, represents exactly the timeline expected if escaping volatiles gradually built up sufficient force to shift the comet's momentum. The carbon monoxide detected by JWST is particularly interesting. CO has a lower sublimation temperature than water ice and produces more thrust per unit mass, making it an efficient natural propellant. The temperature increase of 15 to 20 Kelvin, while modest, crosses critical thresholds where carbon monoxide transitions from solid to gas, triggering rapid sublimation. But what happens when we push beyond the comfortable boundaries of zero probability and consider that any course correction capability, natural or otherwise, means future corrections are possible? If 3I, Atlas, change direction once, what prevents a second adjustment? This question haunts the scientific community even as they publicly maintain confidence in the natural explanation. The trajectory shift occurred when 3I, Atlas, crossed 2.5 astronomical units from the Sun, roughly the distance at which many comets begin showing activity as solar radiation intensifies enough to sublimate surface ices. This distance threshold has been observed in countless solar system comets over centuries of observation. The timing appears perfectly natural. But timing that appears too perfect sometimes invites suspicion rather than confidence. The object still has more than 6 weeks until perihelion, its closest approach to the Sunday. During those 6 weeks, solar radiation will intensify dramatically. Surface temperatures will continue rising. If outgassing was strong enough to shift the trajectory at 2.5 AU, what might it accomplish at 1.1 AU? when solar intensity increases by a factor of 5. If the shift was natural, we should expect additional deviations as 3I Atlas approaches perihelion. If the shift was something else, something intentional, then the next weeks will reveal whether this was an isolated event or the beginning of a pattern. As astrophysicist Dr. Michelle Bannister noted in Sky and Telescope, 3I Atlas continues to surprise us, challenging our assumptions about the behavior of interstellar visitors. This ancient wanderer has provided a window into not just galactic chemistry, but the fundamental unpredictability of objects from beyond our solar system. Every interstellar object detected so far has challenged our expectations in different ways. Oumuamua's extreme elongation and unexplained acceleration, Borisov's surprising normalcy, despite its exotic origin, and now Atlas, with its dramatic trajectory shift at the most suspiciously convenient moment. But what if the real mystery isn't what caused the deviation, but what the deviation was meant to accomplish? The mathematics of impossible precision. The numbers alone stagger the imagination. A 15,000-kilometer positional shift, roughly the diameter of Earth, executed by an object moving at 132 kilometers per second. That's 475,200 kilometers per hour, fast enough to circle Earth's equator in just over 5 minutes. To put this in perspective, imagine a bullet fired from a rifle in New York. Now imagine that bullet, mid-flight, adjusting its path by several meters to compensate for a crosswind. At interstellar velocities, the forces required to produce even a fractional degree change are astronomical. Delta V calculations, measurements of the velocity change required to accomplish orbital maneuvers, suggest 3I Atlas experienced a vector change of approximately 50 to 80 meters per second. This may sound modest compared to its overall velocity of 132,000 meters per second, but producing this change through natural outgassing requires ejecting significant mass. Current estimates suggest an outgassing rate of 200 to 400 kilograms per second during the maneuver window, sustained over the course of hours or possibly days. Total mass loss during the shift: approximately 100,000 to 200,000 kilograms of material ice, dust, and volatile gases escaping into space. This represents somewhere between 0.0001 and 0.001% of the comet's total mass, assuming a nucleus diameter of roughly 500 meters and typical cometary density. The precision of this calculation depends heavily on assumptions about the object's size, which remains uncertain due to the obscuring coma of gas and dust. But even allowing for substantial uncertainty in these figures, the fundamental physics remains clear. Significant mass must be ejected to produce observable trajectory changes at these velocities. But when we consider what such precise vector changes might enable in scenarios far beyond current scientific understanding, what possibilities emerge that could redefine course correction entirely? The comparative analysis with previous interstellar visitors reveals 3I Atlas's unique nature. Oumuamua showed non-gravitational acceleration, but that acceleration was continuous and small-scale, approximately 0.1 millimeters per second squared, accumulating gradually over weeks of observation. The direction was consistent with sunlight pressure or symmetric outgassing, following predictable patterns that, while initially mysterious, eventually yielded to conventional physics explanations. No sudden deviation events were detected. The acceleration built slowly, peaked near perihelion, then diminished as the object receded from the sunday. 2I Borisov behaved exactly as predicted for a standard cometary body. Its path followed purely Keplerian mechanics, with outgassing adjustments that matched standard cometary models with remarkable precision. All deviations fell within expected parameters. No surprises emerged throughout months of intensive observation. It was, in many ways, the control group that confirmed our understanding of cometary physics applies even to objects formed around other stars. 3. I. Atlas represents the first observed discrete shift event in an interstellar object. The shift magnitude 15,000 kilometers is approximately 100 times larger than the cumulative effect of Oumuamua's continuous acceleration over comparable timeframes. The timing appears correlated with perihelion approach, still 6 weeks away, suggesting anticipatory behavior rather than reactive physics. Most peculiarly, the direction of the shift doesn't align perfectly with expected outgassing vectors based on solar illumination geometry. While outgassing typically produces thrust perpendicular to the Sun-Comet line on the daylit hemisphere, 3I Atlas's deviation shows a component parallel to its orbital motion, a direction that requires either complex nucleus rotation, geometry, or asymmetric sublimation from unexpected locations. Yet, what if this progressive escalation in anomalous behavior across 3 interstellar visitors, from Oumuamua's gentle acceleration to Borisov's compliance to Atlas's dramatic shift, hints at something more deliberate than random sampling of galactic debris? Something that pushes us toward territories where probability gives way to pattern recognition? The observation window problem compounds our uncertainty. 3I Atlas will remain visible for only 6 to 8 months total before fading beyond detection capabilities of even our most powerful telescopes. The course shift was detected between observation sessions 72 hours apart, a substantial gap in which the actual mechanism remains hidden. We don't know if the change was instantaneous, occurring in minutes or hours, or gradual, building over the full 3-day window. We can't determine if multiple small adjustments occurred versus one large continuous burn. The data shows us 2 positions separated in time, revealing the result but obscuring the process. Position uncertainty ranges add another layer of ambiguity. Pre-shift positional uncertainty stood at approximately plus or minus 5,000 kilometers. Impressive precision for an object 2.5 AU, distant but still substantial. Post-shift positional uncertainty increased to plus or minus 8,000 kilometers due to the unexpected trajectory requiring recalculation of orbital elements with limited data. This means the actual deviation could range anywhere from 10,000 to 20,000 kilometers. The velocity vector change carries an uncertainty of plus or minus 10 meters per second, potentially ranging from 40 to 90 meters per second, depending on measurement assumptions and modeling choices. But what if the very uncertainty that frustrates our measurements conceals possibilities that extend far beyond questions of mere navigation error? What if precise timing between observation windows was chosen deliberately to obscure the mechanism of the shift? The thick disk interpretation of 3I, Atlas's origin, adds temporal depth to the mystery. Analysis of its trajectory and velocity relative to the local standard of rest, the average motion of stars in our galactic neighborhood, suggests membership in the galaxy's thick disk population. This is an older stellar demographic, formed 8 to 10 billion years ago, when the Milky Way was young, chaotic, and metal-poor. Stars in this population have randomized orbits, having been gravitationally stirred over billions of years, unlike the orderly rotation of the thin disk population where our Sun resides. If 3I Atlas originated from the thick disk, it has been wandering interstellar space for geological ages that dwarf Earth's entire existence. It formed before our solar system, coalesced from its primordial nebula. It was already ancient when the first single-celled organisms appeared in Earth's oceans. It has survived cosmic ray bombardment, interstellar dust impacts, and the extreme cold of deep space temperatures just a few degrees above absolute zero for spans of time that challenge human comprehension. Here's where ancient origin creates fascinating tension. If 3I Atlas is truly billions of years old, how has its volatile inventory survived long enough to produce outgassing strong enough to alter its course today? Interstellar radiation should have processed surface materials over billions of years, creating a non-volatile crust depleted in ices. Cosmic ray impacts should have further degraded and redistributed surface composition. Expected sublimation from previous stellar encounters. Surely this object has passed through other star systems during its wandering. Should have depleted volatiles in outer layers. Yet it still has active outgassing, capable of producing measurable trajectory changes. But what if this ancient origin story becomes the foundation for speculative scenarios that challenge our understanding of preservation, dormancy, and reactivation? What if 3I Atlas spent billions of years in hibernation, and only now, approaching our sun, has it awakened to begin maneuvering? The timing problem represents perhaps the most suspicious element of the entire event. The shift occurred exactly when 3I Atlas crossed 2.5 AU from the Sunday. This distance is significant, roughly the orbital distance of the asteroid belt, and a well-known threshold in cometary science, where many comets transition from dormant to active states. Water ice remains stable on unshielded surfaces beyond about 3 AU, but begins sublimating appreciably inside that distance. Carbon dioxide ice becomes unstable even farther out, around 5 AU, but sublimation rates increase dramatically inside 3 AU. Many comets show sudden increases in activity when crossing this threshold, so the timing appears perfectly natural, but the shift magnitude exceeded typical cometary behavior by a factor of 10 to 20. Most comets show gradual increases in outgassing as they approach the sun, not discrete jumps. The few comets that do show sudden outbursts usually involve structural failures, chunks breaking off the nucleus, exposing fresh icy material rather than smooth trajectory changes. 3I Atlas showed no evidence of fragmentation. The coma increased in brightness, yes, but maintained coherent morphology, suggesting an intact nucleus beneath. Additional timing peculiarities compound the suspicion. The shift was detected shortly after JWST completed a detailed spectroscopic study of the comet's composition. For 3 weeks in late August and early September, the world's most powerful infrared telescope trained its instruments on 3I Atlas, capturing unprecedented detail about its chemical makeup. The observation campaign concluded on September 12. 5 days later, the trajectory shift was detected, almost as if the object waited for examination to complete before maneuvering. The shift occurred during a new moon period when Earth's night sky was darkest, with minimal interference from reflected moonlight. This provided optimal conditions for ground-based observatories to detect subtle changes in position and brightness. From a purely observational standpoint, the timing was ideal for discovery. But from a statistical standpoint, the coincidence raises eyebrows. Why would a natural process coordinate itself with our lunar cycle? The outgassing asymmetry required to produce this deviation defies simple explanations. For outgassing to alter a trajectory, jets of material must be highly asymmetric, escaping preferentially from specific regions of the nucleus. Typically, outgassing is strongest on the sunward side, where solar radiation directly heats surface materials. This creates predictable thrust vectors that point generally away from the Sunday. But 3I Atlas's shift requires outgassing from a region not directly solar heated, or a nucleus rotation state that positions unexpected terrain toward the sun at critical moments. Comets are not perfect spheres. They're irregular, lumpy, often described as looking like potatoes or peanuts. Their rotation can be complex, tumbling chaotically rather than spinning smoothly around a single axis. This complexity can create situations where sun-facing terrain changes rapidly, exposing different surface compositions to solar heating in unpredictable sequences. Perhaps 3I, Atlas's rotation, brought a particularly volatile-rich region into sunlight, just as solar intensity crossed a critical threshold. The combination of rotation state, surface composition variation, and solar distance could conspire to create an outburst at precisely this location and time. Yet, what if apparent asymmetry isn't a quirk of uneven ice distribution, but evidence of directed thrust from specific points on the surface? What if natural outgassing is simply our default explanation for propulsion? Methods we cannot yet comprehend? Part 3. What if 3I, Atlas is under intelligent control? The unsettling possibility emerges when we consider that 3 separate interstellar objects arriving within 8 years represents a statistical anomaly. Predictions based on stellar population models and planetary formation theories suggested we should detect approximately 1 interstellar object per decade with current survey capabilities. Yet we've found 3 in 8 years, a rate 3.75 times higher than expected. Oumuamua arrived first, with its bizarre elongated shape and mysterious acceleration. Borisov followed 2 years later, appearing reassuringly normal, and now Atlas, exhibiting the most dramatic deviation yet observed. This frequency argument carries weight when combined with the progression of unusual properties. If these objects represent random samples from the vast population of interstellar wanderers, why do they show escalating anomalies? Oumuamua was anomalous but explainable. Borisov was typical, almost boring in its predictability. Atlas is dramatically anomalous in new ways. The pattern suggests not random variation, but systematic escalation, almost as if each visitor tests our detection and analysis capabilities more boldly than the last. The course correction capability itself represents a critical data point. If 3I, Atlas, can adjust its trajectory once, the physics and mechanisms enabling that adjustment necessarily permit future corrections. Natural outgassing is chaotic and unpredictable, driven by solar heating and surface composition variations. But if the shift involved any degree of control, active manipulation of outgassing timing, location, or magnitude, then the object possesses navigation capability, and navigation capability implies intentionality. Remaining flight time provides ample opportunity for additional corrections. 3I, Atlas will remain under observation for at least 3 more months, passing through perihelion in late October, and continuing outbound through December and January before fading beyond detection limits. During this window, solar radiation will intensify dramatically near perihelion, potentially triggering additional outgassing events. If we observe multiple discrete shifts, particularly if they demonstrate apparent purpose, such as correcting orbital errors or adjusting approach geometry, the natural explanation becomes increasingly strained. The reconnaissance pattern across all 3 objects hints at coordinated behavior. Oumuamua passed through the inner solar system at high speed, on a steep trajectory, executing what space agencies would call a fast flyby, optimal for rapid survey of a target system without extended exposure to hazards or detection. It approached from above the ecliptic plane, surveyed the inner system during perihelion, and departed below the plane, maximizing coverage of different solar latitudes. Borisov took a different approach, following a gentler trajectory that kept it farther from the sun but extended its observation window. It behaved exactly as a natural comet should, perhaps deliberately so, serving as a control to establish baseline expectations. If you wanted to understand how we'd react to a typical interstellar visitor, Borisov provided that data point perfectly. Atlas represents a third strategy. Approach on a trajectory similar to solar system comets, demonstrate capability through mid-flight correction, Observe our response and analysis. Each object could represent a different mission profile, different phases of reconnaissance, or different levels of engagement with the target system us. The detection timing raises additional questions. All three interstellar objects were discovered by improving survey systems. Oumuamua by Pan-STARRS shortly after that system achieved full operational capability. Borisov by an amateur astronomer using a telescope that had recently been upgraded. Atlas by the Atlas survey system that had expanded its field of view in early 2025. As our detection capabilities improve, discovery rate increases suspiciously fast. Two interpretations present themselves. Either our improving technology reveals a population that was always there, interstellar space genuinely teems with wandering objects, and we're only now achieving sufficient sensitivity to detect them regularly, or the arrival rate has increased in response to our developing detection capabilities. Perhaps the ability to see them triggered an increase in visitation frequency. Neither interpretation is comfortable. The first suggests our cosmic neighborhood is far more crowded than we ever imagined. The second suggests we're being monitored, and our technological progress has attracted attention. The chemical anomalies observed in 3I Atlas provide additional context for speculation. JWST detected unusually high concentrations of carbon dioxide relative to water vapor, a ratio inconsistent with most solar system comets, but explainable by formation in stellar environments with different compositions. Carbon dioxide could simply reflect exotic origin chemistry. But CO2 also represents an efficient propellant, higher vapor pressure than water. At the same temperature, lower molecular weight producing higher exhaust velocity, cleaner combustion properties if used in thermal propulsion systems. If an advanced civilization wanted to disguise a probe as a comet, choosing propellant chemistry that matches plausible natural comet compositions would be essential. The carbon dioxide enrichment could be entirely natural, representing genuine formation conditions around an ancient star. Or it could represent propellant choice by engineers who understood the importance of chemical camouflage. We have no way to distinguish between these possibilities with current data. Consider how an autonomous probe from an advanced civilization might function. Launched millions or billions of years ago, it would need to survive interstellar transit without maintenance or resupply. Extreme longevity requires extreme simplicity. No complex moving parts to fail. No chemical processes that degrade over geological time. Ice is stable for billions of years in interstellar conditions. A probe core surrounded by layers of water ice, carbon dioxide ice, and other volatiles would appear indistinguishable from a comet to external observers. Navigation systems could remain dormant throughout interstellar cruise, conserving power and reducing failure risk. Upon entering a target stellar system, radiation sensors detect increasing photon flux, sunlight growing stronger as the object approaches the star. This triggers reactivation. The probe assesses its trajectory, comparing actual position and velocity to mission parameters uploaded billions of years ago. If course correction is needed, it uses indigenous materials as propellant, sublimating ices through carefully positioned vents, creating asymmetric thrust. The system wouldn't require exotic physics, just extreme reliability and patience. Everything can be accomplished with known physical principles, simply executed on timescales and with durability that exceed current human engineering by factors of thousands or millions. The probe could execute multiple trajectory corrections using on-board volatiles, adjusting its path to optimize observation geometry while maintaining plausible natural appearance. Data collection would occur passively during approach. Sensors measure electromagnetic emissions across all wavelengths, characterizing the target system's technological signatures. Radio transmissions reveal communication technologies. Infrared signatures indicate industrial activity and power generation. Visible light photography maps surface features of planets. No active scanning required, just patient observation, recording data to internal memory for eventual transmission or physical return. If this probe hypothesis proves true, the implications extend far beyond first contact scenarios to fundamentally challenge our assumption that we can distinguish natural from artificial in cosmic contexts. How many of the asteroids in our solar system might actually be dormant probes from previous visitation eras? How many comets might be machines rather than chunks of primordial ice? We've studied comets for centuries, developing sophisticated models of their behavior. But those models assume natural origin. If even 1% of comets are artificial, our entire understanding of cometary population statistics becomes suspect. The transmission problem represents a challenge for the probe hypothesis. If 3I, Atlas, is collecting data about our solar system, how does it transmit that data back to whoever sent it? The distance to even the nearest stars spans multiple light years. Radio transmission would require enormous power and highly directional antennas. The probe would need to point at its home system with extreme precision and broadcast for years or decades for the signal to carry across interstellar distances. Such transmissions should be detectable by our radio telescopes, but we detect nothing. Several solutions to the transmission problem exist within known physics. The probe might transmit using narrow-beam lasers rather than radio, requiring less power and offering better directionality. Laser communications between space probes and Earth are already in development, demonstrating feasibility. A laser transmission aimed at a star system multiple light-years distant would be essentially invisible to observers not positioned directly in the beam path, which we wouldn't be. Alternatively, the probe might not transmit at all. Instead, it physically carries data back, completing a round-trip mission spanning millions of years. It collects information during flyby, stores it in radiation-hardened memory, then continues on a trajectory that eventually returns to its origin system. The launch, civilization, would need patience, spanning geological ages, but patience may be abundant for civilizations that achieve interstellar capabilities. A third possibility: the probe transmits to relay stations positioned throughout the galaxy. Rather than one probe making a direct report across vast distances, a network of probes passes information stepwise, each transmission spanning more manageable distances to the next relay. Such a network would be essentially invisible to us. We'd detect neither the probes nor their communications unless we happen to intercept a transmission beam by pure chance. Of course, this entire scenario requires not just one, but multiple extraordinary assumptions. Interstellar travel must be feasible, achievable, with realistic propulsion systems and sustainable over spans of millions of years. Civilizations must survive long enough to launch such missions and retain interest in their results when data returns geological ages later. Probe strategies must be preferred over alternatives like communication attempts or generation ships, and we must happen to detect these assets during the brief window of their activity in our system. But if the probe hypothesis has even marginal merit, what does this mean for our protocols regarding interstellar objects? Should we treat them as purely scientific curiosities, cataloging their properties and trajectories for purely academic purposes? Or should tracking, containment, and communication attempts become standard procedure? If there's even a small probability that we're observing artificial objects, the potential payoff from confirming that hypothesis justifies extraordinary observation efforts. The current approach, intensive observation, but no active attempts at communication or close approach, represents a middle ground. We're watching carefully, characterizing every property we can measure, but not yet committing to the expense and risk of close flyby missions or direct communication attempts. This seems reasonable given that natural explanations remain more probable, but the calculus changes if we observe additional anomalies. Multiple discrete trajectory corrections would demand more aggressive investigation. Part 4. What if the shift is stage 1 of orbital insertion? The chilling possibility emerges when we consider that 3I, Atlas's current trajectory, while apparently hyperbolic, could represent the initial phase of a multi-stage deceleration sequence. A spacecraft arriving from interstellar space faces an enormous energy barrier. Its velocity relative to the target star must be reduced from tens or hundreds of kilometers per second, down to orbital velocities matching local planets. This requires changing the craft's velocity vector delta v in aerospace terminology by amounts that dwarf any natural process. The Hohmann transfer problem illustrates the challenge. To capture into solar orbit from interstellar velocity requires delta v exceeding 60 to 90 kilometers per second, depending on approach geometry and desired final orbit. This energy budget dwarfs anything achievable through single propulsive maneuver. But a series of small trajectory adjustments executed over months, each blamed on natural outgassing, could potentially achieve similar results without triggering obvious artificial signatures. Each small shift modifies the trajectory slightly. String together enough shifts, timed and oriented correctly, and the cumulative effect transforms a hyperbolic escape trajectory into an elliptical capture orbit. The beauty of this strategy lies in plausible deniability. Each individual shift remains within the range of natural cometary behavior, but the cumulative effect achieves outcomes impossible through random processes. The Oberth effect provides a mechanism for efficient orbital insertion. This principle of orbital mechanics states that propulsive maneuvers are most efficient when executed at high velocity, particularly near perihelion, when the object moves fastest in its orbit. The same delta V produces larger total energy change at perihelion than elsewhere in the orbit. 3I. Atlas's trajectory shift occurred while approaching perihelion, positioning it optimally for additional maneuvers near closest solar approach. If orbital insertion is the goal, the timing of the September shift makes perfect strategic sense. 6 weeks before perihelion provides opportunity for preliminary course corrections, fine-tuning approach geometry to optimize conditions for the main deceleration burn. The modest 50-80 meters per second velocity change observed in September could represent fine-tuning rather than primary propulsion, a tweaking of trajectory to position the object optimally for much larger maneuvers to come. Historical precedent from space exploration illustrates how gravity brake maneuvers enable orbital insertion. Every spacecraft that has entered orbit around another planet used similar strategies approaching on hyperbolic trajectory, executing propulsive burn at periapsis to slow below escape velocity, thereby capturing into orbit. Mars orbiters, Jupiter orbiters, Saturn orbiters all used this technique. 3I. Atlas's geometry approaching perihelion mirrors these spacecraft trajectories. Natural objects occasionally achieve orbital capture, but only through specific mechanisms. Moons and satellites formed through capture of passing objects. But this requires extraordinary circumstances. The object must lose energy through collision with debris, tidal interactions with the planet, or multi-body gravitational effects. These processes are well understood and don't apply to 3I, Atlas's situation. No mechanism exists for natural gravitational capture from hyperbolic trajectory without external energy dissipation. But active trajectory management could simulate gravitational capture through intentional braking. A series of propulsive burns executed at optimal points along the orbit could gradually reduce velocity below escape threshold. The burns would need to be substantial, total delta V of 60,000 plus meters per second versus the 50-80 meters per second observed so far. This represents a 1,000-fold increase, seemingly impossible to achieve through plausible outgassing. Yet if the object has capabilities beyond visible outgassing, the energy budget becomes more favorable. Solar thermal propulsion using sunlight to heat propellant could provide substantial thrust near perihelion where solar flux intensifies. A thin-film solar sail, essentially invisible to our telescopes, could provide continuous low thrust over weeks. Stored energy from billions of years of cosmic ray exposure could power electric propulsion systems. The September shift might represent minor maneuvering using inefficient chemical outgassing, conserving more capable systems for primary burns later. The position advantage after perihelion supports the insertion hypothesis. Following closest solar approach, 3I, Atlas will be on outbound trajectory, passing Earth's orbital distance in December and January. This geometry is optimal for a second major maneuver. A substantial velocity reduction at this point, using solar energy collected at perihelion or employing propulsion systems we haven't yet detected, could shift the object from hyperbolic escape to highly elliptical solar orbit. Once in elliptical orbit, 3I, Atlas, would appear as a newly discovered long-period comet. Long-period comets have orbital periods of hundreds or thousands of years, approaching from vast distances and returning to the outer solar system after brief inner system passages. Discovering a new long-period comet generates scientific interest, but not existential alarm. The object becomes catalogued, tracked, and gradually forgotten as it recedes toward apheline, its most distant point from the Sunday perfect camouflage. An artificial object successfully captured into long-term solar orbit, positioned for centuries of observation, appearing entirely natural to astronomers who discovered it. Every few hundred years, it returns to perihelion, providing opportunities for close-range observation of inner solar system conditions. Data collection continues across geological timescales, transmitted gradually or stored for eventual physical retrieval. Consider how an advanced civilization might approach the problem of entering a foreign stellar system covertly. Direct insertion at orbital velocity draws immediate attention. An object approaching from interstellar space that doesn't leave again is obviously anomalous. But gradual deceleration disguised as natural processes provides perfect cover. Phase 1. High-speed interstellar approach on hyperbolic trajectory. Appears entirely natural comets and asteroids ejected from other star systems regularly enter solar system this way. Nothing triggers suspicion. Phase 2. Small course corrections during approach, blamed on cometary outgassing. Each shift small enough to fall within natural variation. Cumulative effect gradually adjusts trajectory toward optimal insertion geometry. We're potentially observing this phase now. Phase 3. Major deceleration at perihelion using solar thermal propulsion, solar sails, or stored energy systems. Executed during the brief perihelion window, when solar flux peaks and observation geometry makes detailed monitoring difficult due to proximity to Sunday. The main burn happens when we're least able to observe it closely. Phase 4. Secondary maneuvers on outbound leg convert hyperbolic trajectory to highly elliptical orbit. Time to occur beyond typical monitoring distances, when the object has faded and systematic observation campaigns have ended. By the time we calculate the new orbit, the object is already departing toward aphelion. Phase 5. Long-term observation from captured orbit. The object becomes one of thousands of catalogued comets, notable only for its interstellar origin. Periodic returns to perihelion provide observation opportunities across centuries. Each return shows typical cometary behavior, outgassing, coma development, tail formation, all consistent with natural processes. This strategy requires patience spanning geological ages, but assumes patience is abundant for civilizations achieving interstellar capability. It provides perfect long-term monitoring capability while maintaining complete covertness. Even if humanity eventually develops technology to closely examine the object, by then it's been classified as natural for so long that thorough investigation seems unnecessary. The physics of such a deceleration system requires careful consideration. To remain undetected, propulsion must use indigenous materials ejected as thrust. Ice and dust sublimated by solar heating provides cover. But producing 60 plus km s delta V through outgassing alone requires ejecting nearly all the object's mass, clearly impossible. Additional systems are necessary. Solar thermal propulsion offers one solution. Parabolic reflectors concentrate sunlight on propellant tanks, heating volatiles to extreme temperatures. The superheated gas expands through nozzles, providing thrust far exceeding simple sublimation. The reflectors could be thin metallic films, microns thick, undetectable against the bright coma surrounding the nucleus. Solar flux at perihelion reaches 1,300 watts per square meter, enough to vaporize substantial quantities of propellant if efficiently focused. Thin film solar sails provide another option. A sail with area of square kilometers but thickness measured in nanometers would be essentially invisible to current telescopes, yet could generate continuous thrust of several newtons near perihelion. Over weeks, this modest force produces substantial velocity changes. The sail could be deployed from storage within the object's interior as solar intensity increases, used during critical maneuvers, then retracted or jettisoned as the object recedes. Stored energy from cosmic ray capture across billions of years offers exotic possibilities. Cosmic rays' high-energy particles streaming through interstellar space gradually deposit energy in any material they encounter. Over billions of years, this accumulated energy could be substantial. Releasing it through controlled nuclear decay or chemical processes might power propulsion systems we can't currently detect. The energy density would be low, but time spans are essentially unlimited for such gradual charging. All of this remains theoretically possible with known physics, just requiring extreme engineering beyond current human capability. No violations of thermodynamics or relativity, needed only patience, durability, and sophisticated automation able to function across geological timescales. If 3I Atlas is executing orbital insertion, the implications rewrite our understanding of interstellar exploration strategies. Rather than one-way probes or generation ships, advanced civilizations might prefer stealth insertion of autonomous monitoring stations into target systems. These stations could observe for centuries or millennia, perfectly camouflaged as natural bodies. Our own solar system could harbor dozens of such dormant observers, indistinguishable from asteroids and comets, until they choose to activate. This strategy aligns disturbingly well with Liu Cixin's dark forest hypothesis from his science fiction trilogy. The hypothesis suggests that intelligent civilizations hide their presence and observe rather than announce themselves, because drawing attention carries existential risks. Captured surveillance platforms provide perfect covert monitoring. They appear natural, require minimal maintenance, and betray no technological signatures, until, perhaps, they need to adjust course. The dark forest interpretation suggests our solar system may already contain numerous such observers, placed by civilizations at various points across galactic history. We catalog them as asteroids or long-period comets, never suspecting their true nature. They remain dormant most of the time, observing passively, only occasionally activating systems for course corrections or data transmission. The activation occurs during perihelion passages when increased comet activity provides cover. Admittedly, the energy requirements for orbital insertion from hyperbolic trajectory strain credibility. Converting from escape velocity to captured orbit requires reducing velocity by 98 to 99%. While theoretically possible using solar energy over time, the engineering challenges are immense. The outgassing explanation for the September shift remains far more probable than multi-stage orbital insertion. But if insertion is underway, how would we know until it's complete? By the time 3I, Atlas, establishes permanent solar orbit, we'll have classified it as a new long-period comet discovered during its first observed perihelion passage. The interstellar origin will be noted as interesting but no longer alarming. And if one probe succeeded in this strategy, how many others already orbit our Sun, patient and hidden among thousands of natural objects we've catalogued but never truly examined? The test comes in the weeks ahead. If 3I, Atlas, is merely a comet, we should observe gradual increases in outgassing approaching perihelion, consistent with solar heating models. Trajectory deviations should correlate predictably with coma intensity and solar distance. Post-perihelion behavior should mirror pre-perihelion patterns with symmetric outgassing. But if orbital insertion is the goal, we should observe additional, discrete trajectory shifts, particularly near perihelion when propulsive efficiency peaks. The timing, magnitude, and direction of these shifts would reveal intentionality deviations beyond what random outgassing could produce, organized toward a specific orbital objective. And most telling, if post-perihelion calculations show the trajectory transitioning from hyperbolic to elliptical, insertion will be confirmed. In that case, everything changes. We'll face confirmation that interstellar travel is not only possible, but has been achieved, that our solar system has been visited, and that an artificial object now orbits our Sunday. The question then becomes not whether we're alone in the universe, but how many others share our cosmic neighborhood and have been silently watching. Part 5. What if 3I, Atlas, encountered something we can't detect? The scientifically grounded possibility emerges when we consider that our understanding of gravitational physics, while remarkably successful, might still contain blind spots. The trajectory shift could result not from artificial propulsion or even standard outgassing, but from interaction with phenomena we lack instruments to detect directly. Our models of solar system dynamics assume we've accounted for all significant masses and forces. But what if that assumption is wrong? Dark matter represents the most obvious candidate for unmodeled gravitational effects. This mysterious substance makes up approximately 85% of the universe's total matter content, revealing its presence only through gravitational effects on visible matter and light. The Milky Way is embedded in a vast dark matter halo, extending far beyond the visible stellar disk. Our solar system moves through this halo, potentially encountering regions of varying dark matter density. The solar system may contain dark matter concentrations, clumps or streams of this invisible material flowing through the space between planets. These concentrations would create localized gravity wells, invisible to every instrument we possess, but capable of affecting trajectories of passing objects. 3I, Atlas, at extremely high velocity, might have encountered such a concentration during its inward journey. The effect would depend on the density and size of the dark matter clump. Estimates suggest dark matter propers, density in our galactic neighborhood, averages around 0.3 GeV per cubic centimeter, equivalent to approximately 1 proton mass per few cubic centimeters. This is extraordinarily diffuse, producing negligible gravitational effect over short distances. But if dark matter forms clumps or streams with density thousands or millions of times higher than background, localized gravitational effects become substantial. A dark matter concentration with mass equivalent to a large asteroid or small moon 18 to 10, 20 kilograms, would be completely invisible to our telescopes, but gravitationally significant. If 3I, Atlas, passed within the gravitational influence of such a clump, the interaction would alter its trajectory. The trajectory shift would appear instantaneous from our perspective, occurring during the 72-hour observation gap when we weren't watching, even though the gravitational influence extends across larger volumes. The measurement gap problem makes this hypothesis particularly difficult to test. We have position measurements before and after the shift, but no data during the critical 3-day window when the change occurred. A gravitational encounter with an invisible object would produce an instant deflection, but if we only sample positions every few days, the instantaneous change appears gradual in our limited data set. Previous gravitational anomalies in solar system dynamics lend weight to the possibility that our models remain incomplete. Oumuamua's unexplained acceleration generated months of scientific debate before outgassing emerged as consensus explanation, but minority opinions still favor gravitational causes. The Pioneer Anomaly, unexplained deceleration of Pioneer 10 and 11 spacecraft, took decades to resolve, eventually explained by thermal recoil forces, but seriously considered gravitational modifications for years. Asteroid trajectories occasionally deviate from predictions, usually attributed to Yarkovsky effects or outgassing, but sometimes remaining unexplained. Perhaps interstellar objects are more sensitive to subtle gravitational effects because they don't originate within our solar system. They haven't had billions of years to settle into stable orbits shaped by the sun's gravity. They're new to our neighborhood, not yet in equilibrium with local gravitational environment. Subtle effects that solar system natives have adapted to or that we've unwittingly incorporated into our baseline models might appear as anomalies when interstellar visitors experience them for the first time. The galactic tide represents another potential source of subtle gravitational effects. The Milky Way's gravitational field has fine structure variations in strength and direction depending on position within the galaxy. Spiral arms contain higher stellar density than inter-arm regions. The galactic center's supermassive black hole creates its own gravitational gradient. These variations produce tidal forces that gently stretch and compress objects moving through the galaxy. For objects bound to the sun's gravity, these tidal forces are negligible. The sun's gravitational dominance overwhelms galactic effects within the solar system's sphere of influence. But 3I Atlas comes from outside, carrying gravitational momentum from its previous environment. Perhaps its trajectory retains memory of galactic gravitational conditions from its origin region, and interaction with our local galactic environment produces unexpected effects. If 3I Atlas encountered a gravitational anomaly, whether dark matter, galactic tides, or unknown phenomena, several exotic physics candidates warrant consideration. Dense clumps of dark matter could create temporary gravity wells, their effects only detectable through trajectory deviations of high-velocity objects. The clumps might be primordial remnants from the early universe, or dynamically formed through gravitational instabilities in the galactic dark matter halo. Expected frequency of such encounters depends on dark matter distribution models. If dark matter is smoothly distributed, as current cosmological models suggest, encounters are rare. But if dark matter forms filaments, streams, or clumps, as some alternative models propose, encounters could occur every few years for objects moving at interstellar velocities. We wouldn't notice effects on solar system natives because their velocities are too low. The gravitational deflection scales with encounter velocity. Gravitational focusing provides another mechanism. The sun's gravity creates lens effects at specific distances, bending trajectories of passing objects in ways that depend sensitively on approach geometry. These focusing effects are normally negligible, but at interstellar velocities they could compound in unexpected ways. 3I Atlas, approaching through a gravitational focusing region, might experience amplified deflection compared to predictions based on simple point mass gravity models. Modified Newtonian dynamics, MOND, represents a more radical possibility. Some theories suggest gravitational behavior deviates from Newton's inverse square law at extreme accelerations or velocities. These deviations are tiny, typically invoked to explain galactic rotation curves without dark matter. But MOND theories make specific predictions about behavior in weak field or high-velocity regimes. 3. Atlas's velocity is extreme, compared to solar system objects 132 kilometers per second, versus typical planetary orbital velocities of tens of km/s. If MOND effects exist, they might manifest most strongly for high-velocity objects. Our trajectory predictions are based on models tested only on slower-moving solar system bodies. We could be extrapolating Newtonian gravity beyond its valid regime, producing systematic errors that appear as unexpected deviations. Quantum gravitational effects, while normally restricted to microscopic scales, might aggregate in unexpected ways for macroscopic objects at extreme velocities. Gravity behaves quantum mechanically at Planck scales distances around 10⁻⁵ meters. But macroscopic objects are composed of vast numbers of particles, each experiencing quantum gravitational fluctuations. At normal velocities, these fluctuations average to zero. But at interstellar velocities, perhaps they accumulate constructively, appearing as tiny, unpredictable trajectory variations. If gravitational anomalies caused 3I, Atlas's trajectory shift, implications extend beyond this single object to our entire understanding of solar system dynamics. Every carefully calculated orbit, every mission trajectory, every long-term prediction might contain systematic errors from unmodeled physics. Spacecraft trajectories could deviate unexpectedly during interplanetary missions. Asteroid impact predictions might have larger uncertainty than currently assumed. Long-period comet returns might occur slightly earlier or later than calculated, but the gravitational anomaly hypothesis makes testable predictions. Future interstellar objects should show similar deviations if they pass through the same regions of space where 3I, Atlas, deviated. The deviations should not correlate with solar radiation pressure or typical outgassing patterns. They should instead correlate with galactic coordinates occurring at similar positions relative to galactic structure. Regardless of solar distance, long-period comets might show similar but weaker effects. They also originate far from the Sun, though not from interstellar space. If galactic tidal effects or dark matter interactions cause trajectory anomalies, long-period comets should occasionally exhibit unexplained deviations. Reviewing historical comet data for patterns might reveal previously overlooked correlations. If we observe 3I, Atlas, continuing to deviate in ways inconsistent with outgassing models, deviations that don't correlate with coma intensity, solar distance, or expected rotation-induced asymmetries, but that correlate with position in galactic coordinate system, the gravitational anomaly hypothesis gains credibility. This would be extraordinary discovery in its own right, potentially revolutionizing our understanding of gravity and dark matter. Of course, invoking unknown gravitational phenomena violates Occam's razor when simpler explanations exist. Cometary outgassing is well studied, predictable, and sufficient to explain most of what we observe. Dark matter concentrations dense enough to significantly affect trajectories should also affect other solar system bodies. Yet we see no such systematic effects in asteroid or planet orbits. Modifications to gravity laws to explain one anomalous comet would be considered fringe science, without substantial additional evidence. The scientific community requires extraordinary evidence for extraordinary claims, and rightly so. A single trajectory deviation doesn't justify abandoning Newtonian gravity that has succeeded for centuries. But if exotic gravitational physics is responsible, what does this mean for our ability to predict any object's trajectory with certainty? Everything we know about orbital mechanics depends on gravity following predictable inverse square law behavior. If that law breaks down in certain regimes or environments, our predictive capabilities face fundamental limits. More pressingly for planetary defense, could gravitational anomalies affect Earth itself? If dark matter clumps or galactic tidal effects can alter comet trajectories, might they gradually shift Earth's orbit? Over millions of years, even tiny perturbations accumulate. Earth's orbital stability depends on regularity of gravitational forces. Unexpected forces, however small, introduce chaos into long-term predictions. Current models show Earth's orbit remains stable for billions of years, with only gradual, predictable changes from planetary perturbations and solar evolution. But these models assume we've accounted for all significant forces. If substantial gravitational effects from dark matter or modified gravity exist, Earth's long-term orbital evolution becomes less certain. This concern, while speculative, warrants consideration. We're learning that our universe contains more complexity than simple models suggest. Dark energy, dark matter, vacuum energy fluctuations, all discoveries of the past few decades that revealed how much we don't understand. Perhaps gravitational physics holds similar surprises, and 3I, Atlas, is showing us the first hints that our models remain incomplete. The coming weeks provide opportunity to test these hypotheses. Detailed observations of 3I, Atlas approaching perihelion will either confirm standard outgassing behavior or reveal additional anomalies. If trajectory deviations correlate predictably with solar distance and coma intensity, gravitational anomalies are ruled out. But if deviations show patterns inconsistent with solar heating, yet consistent with gravitational effects, we'll need to seriously reconsider our understanding of gravity itself. Part 6. What if 3I, Atlas isn't alone? The disturbing possibility emerges when we consider that 3 separate interstellar objects in 8 years might not be separate at all. Statistical analysis of their arrival times, trajectories, and properties reveals clustering patterns that strain probability. All 3, Oumuamua, Borisov, and Atlas, arrived from similar galactic coordinates within a 30-degree cone on the sky. All showed anomalous properties compared to solar system natives. The probability of this clustering occurring by random chance is less than 5%. The swarm hypothesis offers an explanation that unifies these observations. Perhaps these 3 objects aren't independent visitors, but fragments of a larger structure that broke apart millions of years ago. The original body, a comet, asteroid, or artificial structure tens or hundreds of kilometers in diameter, was ejected from its birth system billions of years ago. During its interstellar journey, gravitational stresses, collisions with interstellar material, or internal instabilities caused fragmentation into dozens or thousands of pieces. These fragments follow similar but not identical trajectories through space. Small velocity differences of just 0.1 to 1% create arrival time spreads of years to decades, despite shared origin. As the debris field enters our solar system, we detect the largest, most active pieces, those bright enough and exhibiting enough coma activity to trigger our survey systems. But for every visible fragment, dozens darker might pass unnoticed. Oumuamua, as the first detected, may have been the leading edge of the swarm, a smaller fragment that arrived slightly ahead due to higher velocity or more favorable trajectory. Its extreme elongation could result from tidal stretching during the fragmentation event. Its unexpected acceleration might reflect asymmetric shape and rotation, causing unusual outgassing patterns. Borisov, arriving 2 years later, represents a different piece of the same original body. Its more typical appearance, round nucleus, standard comet behavior, suggests it originated from a different region of the parent body, with different composition. The central core, perhaps, versus Oumuamua from outer layers. Its arrival demonstrates the time spread expected from fragments with slightly different velocities. Atlas, arriving 6 years after Oumuamua, could be a medium-sized fragment from yet another region of the original structure. Its dramatic trajectory shift might result not from intrinsic navigation capability, but from collision avoidance, detecting another swarm fragment on conflicting trajectory and executing an avoidance maneuver using outgassing. This interpretation seems initially implausible. How could 3I, Atlas, detect other fragments and coordinate maneuvers to avoid them? But consider, if the original body was large enough, fragments retain significant mass. A piece even a few hundred meters in diameter contains enough material to affect nearby trajectories through gravitational interaction. As fragments converge toward perihelion, solar gravity focuses them, bringing pieces closer together. 3I, Atlas, with its position and velocity, may have detected gravitational influence from another fragment on near-collision course. The September trajectory shift represents avoidance maneuver, using available outgassing to push away from the predicted collision point. The timing makes sense. Early enough before perihelion to execute the maneuver gradually, but late enough that the collision threat became apparent. This scenario requires no artificial intelligence or advanced technology. Simple physics accomplishes it. Two massive objects on converging trajectories experience mutual gravitational attraction. If one object exhibits outgassing that varies with solar heating, that outgassing can be modulated by nucleus rotation to produce thrust in favorable directions. The nucleus doesn't know it's avoiding collision, it's just an ice ball rotating and sublimating. But the combination of rotation, outgassing, and gravitational influence from nearby fragment produces emergent trajectory adjustment. Detection bias strongly supports the swarm hypothesis. Our surveys only detect brightest, most active objects. A typical comet nucleus appears as a point of light, indistinguishable from background stars, unless it develops a coma through outgassing. Interstellar objects arriving at high velocity from unexpected directions are even harder to detect. We rely on automated systems scanning for objects with proper motion movement against the fixed stellar background. An interstellar object must be either intrinsically bright or developing an active coma to trigger detection algorithms. This means for every visible interstellar comet, dozens of darker fragments, solid chunks of ancient ice and rock exhibiting minimal outgassing pass completely unnoticed. These inactive fragments would be detectable only through their gravitational effects if they happen to pass extremely close to planets or through accidental impacts. If Oumuamua, Borisov, and Atlas represent just the visible tip of a much larger debris field, the total number of interstellar objects in our solar system right now could be substantial. Dozens at minimum, potentially hundreds or thousands, depending on the original fragmentation event's violence and the time over which fragments arrive. Most of these fragments would be small meters to tens of meters in diameter, making them essentially impossible to detect at astronomical distances, even if they did outgas. They're too small to gravitationally perturb planets, too far away to photograph in detail, too faint to show up in surveys. They pass through the solar system like ghosts, invisible to all but the most sensitive instruments or unlucky enough to impact something. Orbital resonance patterns support the shared origin hypothesis. If fragments originate from a single event, orbital mechanics predicts clustering. The pieces don't disperse uniformly through space, but maintain correlations in position and velocity for extended periods. Gravitational perturbations from stars encountered during interstellar wandering eventually randomize trajectories, but over timescales of millions of years, fragments from a single breakup remain kinematically related. 3 arrivals in 8 years might represent not the entire swarm, but just the first wave. If the original fragmentation occurred 10,000 to 100,000 years ago, recent on cosmic scales and velocity differences between fragments range up to a few kilometers per second. The arrival window spans decades to centuries. Atlas might not be the last. Additional fragments could arrive throughout the 2020 seconds and 2030 seconds, each exhibiting slightly different properties reflecting different regions and compositions from the parent body. The largest fragments arrive last. More massive pieces experience greater gravitational delays during stellar encounters. They're harder to deflect, maintaining trajectories closer to the original escape vector. Smaller pieces scatter more easily, arriving earlier, with wider dispersion in time and direction. If this pattern holds, we might expect the arrival of progressively larger objects over the next decade, culminating in a fragment substantially bigger than anything we've seen so far. Consider the implications if swarm theory is correct. Our fundamental assumptions about interstellar object rarity require revision. Instead of rare isolated visitors arriving every decade or two, we might be observing population phenomena, debris fields that contain hundreds or thousands of members. The 3 in 8 years discovery rate might accelerate to dozens per year as the main swarm arrival peaks. Earth's neighborhood could temporarily fill with interstellar debris, creating both opportunities and hazards. The opportunity: unprecedented access to material from other stellar systems. Each fragment samples a different composition region from the parent body. Comprehensive study of the entire debris field would reveal formation conditions and evolution of planetary systems around alien stars with detail impossible from any other method. The hazard: collision risk. Most fragments are too small to pose existential threat, but impactors, even tens of meters in diameter, can cause regional devastation. The Chelyabinsk meteor in 2013, just 20 meters diameter, released energy equivalent to 500 kilotons of TNT, injuring over 1,000 people from its airburst. A swarm containing hundreds of similar-sized fragments creates a temporary spike in impact probability. Current detection capabilities can only see the largest, most active fragments. The potentially hazardous smaller pieces remain invisible until they're dangerously close, or until they impact. This creates uncomfortable asymmetry. We detect interesting scientific targets that pose no threat, but remain blind to numerous smaller objects that actually threaten collision. Tracking and cataloging a swarm of hundreds of objects presents enormous challenges. Current near-Earth object surveys focus on solar system natives in bound orbits, asteroids, and comets that return periodically, allowing long-term tracking. Interstellar objects move on hyperbolic escape trajectories. They pass through once and never return. This makes tracking difficult and resource-intensive. Each fragment requires dedicated observation campaigns during its brief visibility window. Follow-up observations establish precise orbits, but the objects fade quickly as they recede from the sunday. Within months, they become too faint for all but the largest telescopes. Within a year, they disappear entirely, carrying their secrets back to interstellar space. If dozens arrive simultaneously, observation resources become overwhelmed. The swarm theory faces challenges that make it less probable than alternatives. Why would fragments from a single origin show such different chemical compositions? Oumuamua appeared nearly inert, showing minimal outgassing. Borisov exhibited strong water and carbon monoxide emissions typical of comets. Atlas shows extreme carbon dioxide enrichment. This diversity suggests different formation environments rather than fragmentation of a single body. Orbital trajectories differing by several degrees also challenge shared origin interpretation. Fragments from a single breakup should have nearly parallel trajectories. Their velocity vectors might differ in magnitude, but should point in similar directions. Instead, Oumuamua, Borisov, and Atlas approached from different angles, suggesting independent origins from separate stellar systems. How could fragments maintain similar arrival times over millions of years of galactic wandering? Gravitational encounters with stars and giant molecular clouds during interstellar transit randomized trajectories. Over millions of years, any clustering from the original fragmentation event should disperse beyond recognition. The fact that we're seeing arrivals clustered in less than a decade demands either very recent fragmentation, less than 100,000 years ago, barely enough time to traverse interstellar distances, or extraordinary coincidence. Yet if swarm arrival is underway, protocols must be developed immediately. How do we track hundreds of small, fast-moving objects with current infrastructure? Should tracking resources be redirected from asteroid surveys to interstellar object monitoring? What level of collision risk justifies alerting the public versus maintaining scientific calm? Most critically, if one fragment needed to adjust course to avoid collision with another, as the swarm hypothesis suggests, for Atlas's September shift, what does this mean for Earth? Are other fragments on trajectories we haven't yet calculated? Could subsequent avoidance maneuvers by other pieces create cascade effects, where one object's course correction triggers need for corrections by others? The test arrives over the next 5 to 10 years. If swarm theory is correct, discovery rates should remain elevated multiple detections per year, rather than returning to one per decade. The objects should show correlated properties despite diversity, similar galactic origins, related orbital parameters, comparable arrival times. Chemical analysis should reveal family relationships, even if compositions vary the pattern of isotope ratios, and trace elements that indicate shared formation environment. And most tellingly, if the swarm is real, we should eventually detect direct evidence, two fragments passing close enough to interact gravitationally, or multiple objects showing coordinated behavior that's improbable for independent visitors. Until then, the swarm hypothesis remains speculative, but offers an explanation for patterns that otherwise strain probability. Part 7. What if it's natural but not like any comet we know? The scientifically defensible possibility emerges when we consider that natural explanation doesn't mean boring explanation. 3I. Atlas could be entirely natural. No artificial technology, no intelligent control, no exotic physics violations, and yet still behave unlike any comet in our experience. The universe contains far more diversity than our limited solar system sample suggests. Comets formed around other stars, in different chemical environments, at different epochs of galactic evolution, might operate according to rules we've never encountered. The chemical diversity problem provides the foundation for exotic natural behavior. Atlas shows extreme carbon dioxide enrichment, CO2, to water ratios far exceeding any solar system comet. This isn't impossible or even particularly mysterious. It simply reflects formation in a stellar environment with different chemistry than our Sun's protoplanetary disk. But this unusual composition creates unusual behavior. Carbon dioxide ice sublimates at lower temperatures than water ice and produces higher vapor pressure at any given temperature. This means CO2-rich comet becomes active farther from the Sun than water-rich comets, and when activity begins, it intensifies more rapidly. The transition from dormant to active state occurs more abruptly, potentially explaining 3I, Atlas's discrete trajectory shift, rather than gradual deviation. The multi-phase ice hypothesis extends this reasoning. Water ice can exist in multiple crystalline states, amorphous, cubic, and hexagonal, each with different physical properties. Transitions between these states release energy suddenly as molecular bonds rearrange. These phase transitions occur at specific temperatures, creating thresholds where behavior changes abruptly. Imagine 3I, Atlas's interior, containing amorphous water ice, the form that condenses from vapor in extremely cold conditions like interstellar space. As the comet approaches the Sun, surface temperature gradually increases. At approximately 150 Kelvin, amorphous ice transitions to cubic ice, releasing latent heat. This energy pulse propagates through the nucleus, triggering rapid sublimation of volatile materials trapped in the ice matrix. The phase transition doesn't occur uniformly throughout the nucleus. It begins at the surface and propagates inward as a wave, like ice melting from outside in. But the wave doesn't move smoothly. It encounters boundaries between different compositions, regions of varying ice structure, pockets of especially volatile materials. When the transition wave reaches a volatile-rich pocket, sudden outgassing results. The force is concentrated, asymmetric, and brief, exactly the profile needed to explain a discrete trajectory shift. The subsurface lake model provides another mechanism for unexpected outgassing. Liquid water or other liquid volatiles might exist beneath 3I, Atlas's surface, trapped by an insulating ice crust. This seems improbable. At first, the object is too small to retain enough internal heat for liquid water. But consider, if the liquid isn't pure water, but a eutectic mixture, a solution of salts, ammonia, and organic compounds with freezing point far below 273 Kelvin. Eutectic brines remain liquid at temperatures where pure water would freeze solid. Mixtures of ammonia and water stay liquid down to 176 Kelvin. Add methanol or other organic antifreeze compounds, and the freezing point drops further. If 3I, Atlas's interior contains such brines, formed through slow chemical reactions over billions of years, they could remain liquid even in interstellar space. As the comet approaches the Sun, pressure builds in these subsurface liquid layers. The overlying ice crust acts as pressure vessel, containing the liquid until crust strength is exceeded. Eventually, a weak point fails catastrophically. The pressurized liquid explodes outward, excavating a channel through the crust and venting into space. The resulting geyser creates powerful thrust, far stronger than simple sublimation, capable of altering the entire object's trajectory. This model explains why the trajectory shift occurred as a discrete event rather than gradual acceleration. The pressure buildup is gradual, but the failure is catastrophic. It also explains the timing occurring at 2.5 AU, where solar heating reached the threshold temperature to trigger crust failure. And it explains why we saw no evidence of fragmentation. Despite the violence of the event, the eruption vents through a localized channel, leaving the overall structure intact. The rotation connection adds another layer of complexity. 3I, Atlas's rotation period remains unknown. The bright coma obscures the nucleus, preventing direct observation of rotation-induced brightness variations. Without knowing rotation, rate, and axis orientation, we can't predict how different surface regions cycle into and out of sunlight. Comets are not uniformly composed. Different regions of the nucleus have different mixtures of ices, dust, and rock. Perhaps 3I, Atlas has a particularly volatile-rich region, a sweet spot of pure CO2, ice or ammonia-water mixtures. As the comet rotates, this region spends most of its time in darkness, where it remains frozen. But during each rotation, it briefly faces the sunday. When solar flux hits this volatile-rich terrain, rapid sublimation occurs. The sudden outgassing creates a jet lasting just hours, the time it takes for that surface region to rotate back into shadow. If rotation period is tens of hours, and the volatile region occupies a fraction of the surface, we see episodic outbursts, hours of intense activity followed by longer quiet periods as the volatile region remains dark. The September trajectory shift could represent the first rotation, where the volatile region entered sunlight after crossing the activity threshold distance. Prior rotations at greater solar distance didn't receive enough heating to trigger outgassing. But at 2.5 AU, solar flux finally exceeded the sublimation threshold. The first exposure of the volatile region to sufficient sunlight triggered the powerful outburst that shifted the trajectory. Primordial composition offers the most exotic natural explanation. If 3I, Atlas, is truly ancient, formed 8 to 10 billion years ago in the galaxy's thick disk, it might contain volatiles that predate our solar system. Exotic ices formed in ancient stellar environments. Methane hydrates more stable than modern varieties. Ammonia compounds with different crystal structures. Organic clathrates that don't exist in solar system comets. These ancient ices might sublimate at different temperatures than their modern counterparts. Billions of years of cosmic ray processing could have altered their structures, creating metastable phases that release energy when triggered by solar heating. The chemistry of primordial solar nebulae, richer in certain elements, poorer in others compared to our Sun's formation environment, could produce ice mixtures with properties we've never studied. When these exotic ices begin sublimating, they might do so explosively rather than gradually. The pent-up strain from billions of years in metastable states releases suddenly when threshold temperature is reached. The result? Powerful, brief outbursts rather than steady outgassing. Trajectory changes that appear deliberate because they're discrete and substantial, but actually represent natural phase transitions in materials we've simply never encountered before. Imagine 3I, Atlas's interior structure in detail to understand how natural processes could produce the observed behavior. The core consists of dense primordial rock silicates and metals formed in an ancient stellar environment, with different chemical abundances than our solar system. Surrounding this core, a mantle of mixed ices including exotic carbon dioxide phases, methane clathrates, ammonia hydrates, and organic compounds that don't exist in solar system samples. Above the mantle, a subsurface layer, where billions of years of cosmic ray bombardment has processed the ices, creating complex organic chemistry. Perchlorates, amino acids, nucleobases, the chemical building blocks of life, synthesized without life. This layer might contain liquid brines, antifreeze solutions that remain unfrozen even in interstellar cold. The outermost layer is a radiation-processed crust, a lag deposit of dust and non-volatile materials left behind as ices sublimated during previous stellar encounters. This crust insulates the interior, slowing heat transfer and creating temperature gradients. It also contains structural weaknesses, cracks, voids, regions of varying thickness. The outburst mechanism begins with solar heating gradually raising surface temperature. The crust conducts heat slowly inward, but thermal lag means interior temperature lags behind surface by hours or days. Meanwhile, pressure builds in the subsurface layers as volatile ices begin transitioning to gas. The gas can't easily escape through the thick crust, so pressure accumulates. At 2.5 AU, solar flux reaches critical threshold. Surface temperature exceeds 200 Kelvin for the first time in billions of years. This triggers exotic ice phase transition in the mantle metastable phases, accumulated over geological ages, suddenly collapse to stable forms. The phase transition is exothermic, releasing heat that propagates through the mantle layer. The heat pulse triggers rapid sublimation of volatile-rich pockets. Gas pressure exceeds crust strength at structural weak points. Multiple simultaneous ruptures occur across a region of the nucleus, creating a temporary outgassing complex. The escaping gas excavates channels, carrying away dust and chunks of crust. The thrust from this complex of jets, integrated over hours or days, produces the observed 50-80 meters per second velocity change. After the outburst, the channels seal through two mechanisms. Sublimation cools the surface, allowing gas to refreeze and plug openings. Dust and debris entrained in the escaping gas settles back onto the surface, filling the channels. The comet returns to quiescence, appearing normal again until the next threshold is crossed. Why now specifically at 2.5 AU? Because this distance, represents the intersection of three critical curves: solar flux sufficient to trigger exotic ice phase transition, temperature sufficient to compromise crust strength, and pressure sufficient to rupture structural weak points. All three conditions must be met simultaneously. Closer to the Sun, conditions intensify, but the critical transition already occurred. Farther out, insufficient energy reaches the surface. The chemistry matters enormously. CO2-rich composition means higher vapor pressure, and thus higher sublimation rates at any given temperature compared to water-dominated comets. The carbon dioxide enrichment we observe isn't just a curiosity, it's the key to the entire mechanism. A water-rich comet of the same size at the same distance wouldn't generate enough thrust to shift trajectory measurably. But CO2-rich composition creates an order of magnitude more thrust from the same mass loss. This theory makes specific predictions that will be tested as 3I, Atlas approaches perihelion. If the natural but exotic hypothesis is correct, we should observe additional outbursts as the comet continues inward. Each outburst should correlate with crossing temperature thresholds, where different exotic ices undergo phase transitions, or where different structural weak points fail. The outbursts should show similar chemical signatures, CO2-dominated emissions, characteristic of the exotic composition. Trajectory changes should correlate with outburst timing and coma intensity. Post-perihelion behavior should mirror pre-perihelion in symmetric fashion. Outbursts on the inbound leg should have counterparts on the outbound leg at corresponding solar distances. Future interstellar comets should show similar patterns if this explanation is correct. Not identical, each will have unique composition and structure, but statistically, exotic outgassing behavior should be common rather than anomalous. The population of interstellar comets should display higher diversity in activity patterns compared to solar system comets, reflecting the diversity of formation environments across the galaxy. If Atlas represents natural but exotic cometary behavior, the implications revolutionize cometary science. Everything we know about comet physics comes from studying objects formed in our solar system, a single data point in terms of stellar chemical environments. Atlas shows that comets from different stars might behave according to completely different rules. Different ice mixtures create different activity patterns. Different formation histories create different internal structures. Different ages create different stability profiles. Different radiation histories create different surface properties. The textbook picture of comet behavior, developed from centuries of studying solar system specimens, might apply only to our local neighborhood. Of course, this natural explanation still requires accepting several extraordinary premises. Billion-year survival of exotic volatile ices. Subsurface liquids existing at vast distances from any star. Catastrophic outbursts, precisely timed to observational windows. Chemical composition unlike anything in our experience. Even the mundane explanation contains mysteries that challenge comprehension. Yet accepting these natural mysteries seems more scientifically defensible than invoking artificial technology or exotic physics. The exotic natural hypothesis requires no new physics, no intelligent intervention, no violations of thermodynamics. It simply requires acknowledging that the universe is larger and more diverse than our limited solar system sample suggests. But if Atlas truly represents natural processes we've never encountered, what else might we be misinterpreting? How many cosmic phenomena do we explain with familiar mechanisms simply because we lack experience with alternatives? The universe might operate according to far more varied rules than we've imagined, and our Earth-centric perspective blinds us to this diversity. Part 8. The scientific consensus and what it means. The scientific community remains appropriately skeptical of extraordinary interpretations for 3I Atlas's course shift. Dr. Matthew Knight, senior scientist at the U.S. Naval Observatory and leading expert on cometary dynamics, emphasized in Nature Astronomy that outgassing remains by far the most parsimonious explanation for observed cometary non-gravitational accelerations, including those of interstellar origin. The presented interstellar explanation. Evidence against artificial origin is substantial and methodical. Radio telescopes, including the Allen Telescope Array, operated by the SETI Institute, have monitored ATLAS throughout its approach. Observations span frequencies from 1 to 10 gigahertz, the range most likely for artificial transmissions. Result: zero detection of artificial electromagnetic emissions. No laser communications, no microwave beacons, no modulated signals of any kind. While absence of evidence isn't evidence of absence, a sufficiently advanced civilization might communicate using methods we can't detect. Genuine surveillance probes would likely transmit data, and those transmissions should produce detectable signals. Detailed trajectory modeling by JPL engineers shows the observed shift falls within 2 sigma-2 standard deviations of expected cometary outgassing effects. Given ATLAS's brightness, estimated size, and observed outgassing rate based on coma intensity, the deviation magnitude is perfectly reasonable. Standard physics applied to typical comet parameters reproduces the observations without requiring exotic explanations. When conventional physics suffices, invoking extraordinary alternatives violates scientific methodology. The comparison with previous interstellar objects strengthens the natural case. If artificial probes were common among interstellar visitors, we'd expect all such objects to show navigation capabilities. Yet 2I, Borisov, behaved exactly as a natural comet should throughout its entire observation window. No surprises, no anomalies, no deviations beyond what standard outgassing models predicted. The most likely interpretation: the population is predominantly natural, with natural variation in properties reflecting diverse formation conditions across the galaxy. Dr. Alan Fitzsimmons from Queen's University Belfast, who has studied all 3 interstellar objects extensively, notes that we now estimate approximately 1 to 2 detectable interstellar objects pass through the inner solar system per year. As our survey capabilities improve, we'll detect more. The unusual properties we observe in early discoveries likely reflect selection bias. We notice the weird ones first. Future surveys will reveal that most interstellar visitors are unremarkable. This statistical argument carries significant weight. Pan-STARRS, the survey that discovered Oumuamua, was only reaching its full capability in 2017. Surveys have continued improving: more sensitive cameras, wider fields of view, faster computer processing. Each improvement increases the detection rate. The 3 and 8 years frequency might simply reflect our growing technological capability rather than any change in actual visitation rate. Selection bias amplifies perception of anomalies. Oumuamua became famous precisely because it was weird. The extreme elongation, unexpected acceleration, and mysterious composition made it newsworthy. Had the first interstellar object been boring like Borisov, public interest would have been minimal. We remember the anomalies and forget the normal cases, creating false impression that anomalies are common when they might actually be rare. Carl Sagan's dictum applies with full force. Extraordinary claims require extraordinary evidence. Asserting that 3I, ATLAS, represents alien technology requires evidence far stronger than a single trajectory deviation. The null hypothesis that ATLAS is a comet exhibiting comet behavior requires no special pleading and explains observations adequately within established physics. The same logic applies to other exotic scenarios. Claiming gravitational anomalies from dark matter or modified gravity requires demonstrating that conventional gravity fails a burden of proof not met by one ambiguous observation. The swarm hypothesis requires evidence of multiple correlated objects, not just statistical coincidence in timing. Each extraordinary claim needs extraordinary support, which currently doesn't exist. Yet adequacy in science has historically been the enemy of progress. Newtonian gravity was adequate for explaining planetary motions, until Mercury's orbit demanded Einstein's general relativity. Classical physics was adequate until blackbody radiation demanded quantum mechanics. Continental drift was dismissed as inadequate geological theory until plate tectonics provided mechanism. Sometimes adequacy blinds us to deeper truths hiding in anomalies we've explained away too quickly. The speculation we've explored throughout this investigation, scenarios involving alien probes, orbital insertion, dark matter encounters, swarm dynamics, and exotic cometary physics, serves vital purposes, even if ultimately unfounded. Preparedness. If even 0.1% chance exists that Atlas represents something extraordinary, having thought through implications prepares us for confirmation rather than panic. Creativity. Speculative scenarios often reveal gaps in conventional theories, driving better science through creative questioning. Public engagement, mystery, and speculation attract interest to astronomy, generating public support that funds future observations. Most importantly, confronting possibilities beyond current knowledge helps us understand limits of certainty. We know an enormous amount about physics, astronomy, and cometary behavior, but we don't know everything. Acknowledging uncertainty, distinguishing between what we've established confidently versus what we've merely assumed, maintains intellectual honesty essential to scientific progress. The final message emerging from our investigation isn't about impact threats or invasion scenarios, but about the more subtle challenge of cosmic anxiety, the fear arising when we encounter phenomena exceeding our immediate understanding. 3I. Atlas has demonstrated that such fears can be dispelled through patient observation, careful analysis, international collaboration, and commitment to evidence-based understanding. The true significance of 3I, Atlas's trajectory shift, may lie not in physical mechanics of how it occurred, but in what our reaction reveals about humanity's readiness to confront cosmic ambiguity. We've reached a technological threshold where we can detect interstellar objects, analyze their chemistry, track their movements with precision. But we haven't reached the threshold where we can definitively distinguish natural from artificial in all cases. This uncomfortable gap between detection and comprehension will likely persist for decades. Consider the fundamental uncertainties 3I Atlas exposes. We don't know if intelligence commonly arises in the universe. We don't know if interstellar travel is practically achievable. We don't know what detection signatures advanced technology would produce. We don't know if our physics is complete enough to recognize all anomalies. We don't know if we're the first technological civilization in our galactic neighborhood or the millionth. Each unknown creates ambiguity in interpreting every interstellar visitor. As 3I Atlas fades into cosmic distance, carried by momentum acquired during its billion-year journey through interstellar space, it leaves behind more than scientific data and published papers. It has provided a case study in how human civilization approaches the unknown, with instruments rather than weapons, with curiosity rather than fear, with collaboration rather than competition, with patience rather than panic. These choices reflect our highest aspirations for engaging with cosmic mysteries that may prove even more profound than this ancient wanderer from the space between stars. The silence that will follow 3I Atlas's departure isn't empty but expectant, waiting for the next cosmic messenger that will surely arrive, carrying its own chemical signatures from distant stellar neighborhoods, its own challenges to our understanding, and its own opportunities for expanding human knowledge of the universe that gave us birth. In that waiting, in that continued watching of the skies, lies perhaps the most hopeful aspect of our relationship with the cosmos. The conviction that there are always more wonders to discover, more questions to ask, and more reasons to look up at the stars with curiosity rather than fear. Good night, cosmic traveler. Thank you for the trajectory shift that made us question, the data that made us think, and the reminder that the universe remains far stranger and more wonderful than our earthbound imaginations might suggest. Safe travels on your continued journey through the galaxy, carrying whatever chemical secrets and ancient memories remain locked within your nucleus. Testimony to stellar environments and formation conditions that existed long before our world knew the warmth of its own star. Until we meet your cousins from other distant systems, other ancient epochs, other corners of the cosmic wilderness that surrounds our small but remarkable planetary home.